Hi, everyone. My name is Ellie Lan.
My name is Yao Chen.
And we're here with our teammates, Gu Wei and Qin Di. We're from the University of North Carolina, Chapel Hill, and we're here to present our solution to the Informs portfolio optimization problem. So our presentation has three parts to it. The first part consists of the modified model and the algorithms that we use to solve this model. The second part consists of our experimental results, and finally followed by our conclusions. So we're not oblivious to the fact that we're one of the last teams to go, so we won't bore you with the problem formulation once again. But very briefly, this is the original model that was given by the problem statement. We seek to minimize the objective function such that the linear and quadratic constraints are well satisfied. At the same time, we seek to satisfy the cardinality constraints. Here, linear and quadratic constraints are both continuous, so we decided to treat them as penalties in the objective function. Basically, if any of the continuous constraints are not satisfied, then the objective value will be penalized. Otherwise, if there are no violations, then the penalty is set to be equal to 0. So the new objective function takes into account the old objective value as well as the penalty. So we only need to consider the cardinality constraints when we search for a feasible solution that minimizes the objective function. And we decided to use simulated annealing to approximate the global optimum of the objective function. Our simulated annealing algorithm has the convenience of giving us a fixed return, which makes our job of optimizing lambda a more efficient one. Lambda here is the tuning parameter, and it's the tuning parameter between expected returns and variance. Now I will give a brief overview of this algorithm. So imagine for a second that this is the solution space, and we begin on the starting vertex. Assuming that we don't land on the optimal vertex in our initialization, we search around the neighbors to find a more optimal solution. Now, suppose we choose A as our next point. If the objective value of A is better than the current objective value, then we accept A, and we set the current objective value to be the objective value of A. So now the vertex has been updated from O to A, and we iterate on these steps. And now suppose we reach B. However, because the objective value of B is not lower than that of A, we're confronted with two possible choices. We can either reject B or we can accept B. In the event that we reject B, this means we look in the neighbors of A to find a better solution than B. And let's say that in this case we're very lucky in that we search for a better destination, we actually reach the optimal solution. However, let's pretend for a second that we're not so lucky, and in that we reached a not so great vertex whose objective value is far inferior to that of A. We still want to allow for these unlucky scenarios, but still eventually reach the optimal vertex. And we allow for this by assigning a probability of P to B if we were to reject B, and then assigning a probability of 1 minus P to B if we were to accept B. So this allows for the possibility of still getting to the optimal vertex eventually using an indirect route. What this demonstrates is that even if we reach a not so optimal neighbor, as in the case of B, we can still eventually reach our optimal vertex. And we want to keep this as an option because we want to avoid getting stuck at a local optimum in order to reach the global optimum. So how does this algorithm operate in the specific context of choosing stocks for portfolios? The yellow here represents the selected stocks, and the white represents the unselected stocks. There are a few possibilities when it comes to the updates. First, in this scenario, all three weights are updated. So the W's are the weights, the alphas are the expected returns, and this is how we updated the weights. We update 3 weights at a time, so that's why you have W1, W2, and W3. Now, in the second scenario, the cardinality constraints, which are represented by the gray bar here, allows for 6 active weights, but our portfolio only has 5 active weights. In this case, we add another stock to the portfolio. However, say that the cardinality constraint requires that we only have 5 selected stocks, but we have 6 selected. Then what we do is we just exclude a stock by giving one of the stocks a 0 weight. Now, this eventual result allows us to have a cumulative weight of 1 while satisfying all cardinality constraints. I will now allow my teammate to go over this slide.
Well, the simulated annealing is a very good approach. But here, there's one problem, because it is very sensitive to the initialization and may take more than 3 minutes to achieve the best solution. Therefore, here, we use genetic algorithms to find the smart initialization to the simulated annealing. Okay, so first, we initialize the population which is a set of feasible solutions. And then we pick 2 solutions from the population, which is known as mother and father. And then we use the crossover and mutation operations to produce a new feasible one, which is known as a child. And here is the rule that governs our algorithms. We first check to see if this stock is in our portfolio. And the yellow marks the stock is selected, and the white means that this stock is not selected. And then we randomly pick a stock from the mother or from the father. But here we have to make sure that all the while the cardinality constraint is satisfied. And so in this case, we end up with a child portfolio with 3 selected stocks and only 1 unselected stock, because here the cardinality constraint is 3. The next step is to apply the mutation operation on the child portfolio, which is just multiplying it by a number, either enlarge the weight or shrink the weight. So after it is done, we put this child portfolio into the population, and we iterate this process. And finally, we choose the solution which has the best objective from the population. And we use this as the smart initialization to the simulated annealing. Okay, now let's take a look what's the performance of our algorithm. So first, let's review. This is our modified problem. The eta here is the weight given to the penalty, which is set to be 10,000. And we tested our algorithms on the data from first month. And the iteration here is set to be 12,000 in order to satisfy the 3-minute time requirement. And see, the x-axis here is the number of iterations, and the y-axis here is the objective value, which is in the log scale. And let's look at the chart. We can see that the result with smart initialization outperforms significantly compared to that without the smart initialization. And see, there is a very big jump in the middle of this chart, which is in red. The reason for that is that after a certain number of iterations, in this case is 6,000, our algorithm satisfies all the constraints and achieves 0 penalty. And so we find that our algorithm has a very good performance on the modified problem. But here, what we care about is the original one. So in order to evaluate the original objective, we analyze the expected return and variance individually. So first, expected return. Alpha here is the expected return of all the stocks in this month. And here we use 2 criteria consisting of alpha max and alpha min to evaluate the expected return of our portfolio. So the alpha max is the maximum expected return of all the stocks in this month, and the average expected return is the average expected return of all the stocks in this month. So now let's see how our portfolio compared to that alpha bound and the average. We plot our results across the entire time span of all the data set. And the yellow is the alpha max, which is the alpha bound. And our portfolio is in red, and the average is in blue. So we can find that our portfolio is really close to the alpha bound and beats the average substantially. And now let's turn to the variance part. We again plot the result across the entire time span of all the data sets. And here notice that the constraint 11 requires the variance to be larger than 0.0025, which can be regarded as the lower bound for the variance. And this is yellow in the figure. And from the chart, we see that except for a few months that the variance crossed below the lower bound, for most of the months, the variance remain above and very close to the lower bound. So we can say that our result is very close to the best solution we can possibly get while satisfying almost all of the constraints. And now let my teammate Ali to talk about how it performs on the real-world return data.
So the vector R here is the vector consisting of returns for all of the stocks in the portfolio for a certain month. The second return is the return of our portfolio, which is calculated by multiplying a vector returns by the portfolio weights. Cumulative return is the aggregate sum of the portfolio returns. Now, this is the cumulative return performance of our portfolio that we created in our first attempt, and the orange is the benchmark, and the red is our portfolio. So as you can see, in our first attempt actually underperformed. But we learned from our first attempt, and we created better portfolios in subsequent attempts, namely Portfolio 2 and 3. So Portfolio 2 has a penalty coefficient of 1,000. Portfolio 3 has a penalty coefficient of 10,000. And the coefficient here represents the weight given to the penalty. So a lower penalty translates to a higher tolerance for not satisfying constraints. In both of these portfolios, we invert the sign of the alpha, and we'll explain why we did this on the next slide. But looking at the chart here, Portfolio 2, which uses a penalty coefficient of 1,000 and an alpha that is negative, outperformed all of the portfolios, including the benchmark, substantially. So that by 2016, our Portfolio 2 outperformed the benchmark by 150 bips. Although ideally we like to see a positive relationship between actual and expected returns, past performance teaches us that there's actually an inverse relationship between the two for our given data set. We were interested in investigating this inverse relationship between real return and expected return. However, before we can look into it, we must normalize the returns and alpha so that they're on the same scale. To compare the weekly return versus the alpha, we use this formula to normalize. Now, this is a plot of expected returns versus actual returns after normalization. You can see that there's a clear negative relationship between the two returns. So even though the discrepancy between real and expected returns is somewhat surprising, this phenomenon has been well documented in the past. Expected returns is the average of a probability distribution of possible returns, while actual return is what investors receive from their investments. And both systematic and unsystematic risk factors may contribute to this discrepancy. And lastly, a few key conclusions. Our model solved for the optimal solution very well while satisfying all of the constraints. The return in the objective function very closely approximated the upper bound, while the risk in the objective function closely approximated the lower bound. So the result is optimal in terms of both variance and return. We experimented with many different parameters and on different sets of data, and what we're actually very glad about is experimenting on real return data. What we thought was worth noting was the negative relationship between real and expected returns, and we appreciate your time for listening.